Okay. All right. Let's start now. Okay. Today we will finish the last section of chapter 6. The title is Sampling Distribution and the Central Limit Theorem. Okay. Let's start here. You now have most of the skills to start statistical inference, but you need one more concept. First, it will be helpful to state what statistical inference is more accurate terms. Okay, the first one, the definition, statistical inference. What is that? To make accurate decision about parameters for statistics. Okay, the key word is making decision. But how can we make a decision? We need enough evidence. We need enough information. And this kind of word is called statistical inference. And when it says accurate decision, you want to be able to measure how accurate. You measure how accurate using probability. Okay, probability. And later, this concept is pretty important because next week, we will introduce a concept called p-value. The p-value, the p is standing for probability or possibility. They are okay. If I make a decision, I will calculate, for example, if I go to buy a lottery tonight, I will calculate the probability I won the first prize. Very, very, very low. But if I just win maybe $200,000, I think the probability is much higher than the first prize. Okay, we need to calculate the probability, not only rely on God, rely on luck. Okay, in both binomial and normal distributions, you needed to know that the random variable followed either distribution. You need to know how statistic is distributed, and when you can, then you can find the probabilities. In other words, you need to know the shape of the sample mean or whatever statistic you want to make decision about. Okay, and now let's check the definition. Sampling distribution. What's that? Okay, sampling distribution. How a sample statistic is distributed when repeating trials of the size n are taken. Okay, if we try n times, or many times, and sure, the n just a symbol to mean many times. It can be 1, 2, 3, 4, 5, maybe 1,000, 2,000, 20,000. Okay, and we will get the sampling distribution. Previous sections we discussed about the normal distribution. But remember, not everything, not every type of measures are distributed normally, and we emphasize that only normal distribution samples we can do different calculation. Okay. Example, suppose you throw a penny and count how often a head comes up. The random variable is x equals the number of heads. Okay, the probability distribution, PDF. PDF is not a file name. It's a probability distribution. We call it PDF. Okay. Of this random variable is represented in figure 6.5.1, like this one. Probability distribution for the number of heads. Theoretically, if the coin is fair coin, fair dice, fair star, fair tool, the distribution should be equally showed on head and tail, and thus the probability is 0.5, 0.5. 0.5 for the 0, 0.5 for the 1, 0.5 for the head, 0.5 for the tail. Okay. And solution. Repeat this experiment for 10 times, which means n equals 10. And here is the data set. The data set 1110000, like this one. It means this sample is 0.4. And now take another sample. Here is the data 1110101, like this one. This time the one, I mean the head of the coin, it appears 6 times in 10 trials. Thus, the probability is 0.6. I think it's simple for you. And another 10 times of throwing, and we get this one, 7 heads, 7 heads. Repeat this 40 times, you can get these means like this one, okay? Thus, we can know that the sample means when n equals 10, and if it is assumed this is a real test, and the person throw totally 400 times of the coin. Okay, example here, 6.5.2 contains the distribution of the sample means. Just count how many of each number there are, and then divide by 40, obtained by the relative frequency, like this one. Sample mean here, sample mean, like this one. And probability 0, 0, 0, 0.5, 0.2, 0.175, like this one. And contains the histogram of this sample means, like this one. 0, 0.1, probability 0, 0.2, the probability here 0.05. Mean number of the heads 0.3, and the probability is 0.2, like this one. Then if we have enough time to throw it with the unlimited times, then it becomes a normal distribution. Like this one, PDF for sample means of the heads. Okay, then let's move. Note, suppose you have a random variable that is a population mean, mu, and a population standard deviation, sigma. If a sample size n is taken, then the sample mean x bar have a mean, the mean of the x equals mu, and the standard deviation like this one. Please note that the denominator they use n instead of n minus 1. The standard deviation x bar is lower because taken the mean, you are averaging out the extreme values, remove some outliers, which makes the distribution of the original random variable spread out. Okay, and okay, that's the title of this section. Theorem, central limit theorem. What does it mean? Suppose a random variable is from any distribution. If a sample of size n is taken, then the sample mean x bar becomes a normal distribution as n increases. Again, according to the size, we have two kinds of terms. The first one, population. The second one is called samples. And if the sample size n is taken, then the sample mean x bar becomes normally distributed as n increases, very close to the population distribution. Okay. In other words, if you have enough skills, enough money, enough labor, enough time, you should try the sample number, and the bigger the better. Sure, it's impossible for us to have enough time, to have enough budget, to have enough laborers to do this. Thus, there is a reasonable calculation. Later I will tell you. Okay, what they say is that no matter what x looks like, x bar will look normally if n is large enough. And now, what size of n is large enough? That depends on how x is distributed in the first place. If original random variable is normally distributed, then n just needed to be 2 or more data points. If the original random variable is somewhat mild, shape, and symmetric, then n need to be greater or equal to 30. And generally, when I was a student, the professor told us, if you cannot memorize too much details, you can memorize a number 30, simple number 30. Okay. Sometimes the sample size can be smaller, but this is good rule of thumb. The sample size may have to be much larger if the original random variable is really skewed one way or another. Okay, then now you know that when the sample mean will look like a normal distribution. Okay, do you remember how to judge whether a set of data is a normal or not a normal distribution? Yeah, last time, previous section we discussed about that. If you forgot that, you can review the previous, or you can check the textbook. Okay, then you can find the probability related to the sample mean. Okay, remember that the mean of the sample mean is just the mean of the original data. Ooh, okay. Again, the mean from the sample when the number is larger enough, we can consider this also the population mean. But the standard deviation of the sample mean, sigma x bar, also known as the standard error of the mean, is actually sigma x bar, like this one. Make sure you use this in all calculations. If you are using the z-score, the formula when working with this one, when n z-score like this one, If you're using the calculator, you will get this. Okay, let's move. Example 6.5.2, finding probability of sample means. The birth weight of boy babies in European descent when delivered at 40 weeks is normally distributed with a mean of 3687.6 grams of a baby boy. Okay, with a standard deviation of 410.5 grams. Okay, suppose there were 9 European descent babies born on a given day, and the mean birth weight is calculated. First one, state a random variable. What is the mean of sample mean? What is the standard deviation of the sample mean? What is the distribution? What distribution in the sample mean distributed as? Find the probability. Okay, let's review the question. The birth weight of a baby babies in European descent who were delivered at 40 weeks is normally distributed with a mean like this one. So from this sentence, we may consider it's a population mean. We may consider it's a sample mean. Okay, with a standard deviation of 410.5, we can consider it's a sample standard deviation or it's a population standard deviation. Sure, but after this kind of technology, I believe this could be the population mean and population standard deviation. Okay, solution. First one, X equals birth weight of boy babies. Okay, then next, the mean is equal to a population mean that is 3687.6 grams, and the sample sigma we can consider is also the population standard deviation. Thus 14.5 divided by square root of 9. Square root of 9. Because why square root of 9? Because 9 here, 9 boy babies were selected. Okay, and we got the sigma. We got sigma. We got sigma about this. Okay, then since the original random variable is distributed normally, then the sample mean is distributed normally. Okay, again, the original random variable is distributed normally. We consider the population is a normal distribution, and now we select some samples. We also consider samples are normal distribution. Okay, and question E, you are looking for the probability that the body weight is less than 3,500.4 grams, like this one. Okay, how to calculate this? The probability calculated like this one, and like this one, the probability is close to 0.086. Or you can use R to get this. Okay, let's move. And the next question, find the probability at the mean weight of the 9 babies was less than 3452.5. Again, 9 babies randomly selected from the population, and we can find the average, the mean of 9 babies, less than this one. Okay, there is a 8.6% chance that the mean of birth of the 9 babies born will be less than 3,500.4 grams. Since there is more than 5%, it's not unusual. And next question, the 9 selected babies, their body weight average is less than 3452.5 grams. And run the calculation. Sure, I think this part is okay. Maybe you don't need to practice this part. Okay, and the chance that the mean birth weight of the 9 babies born will be less than 3452.5 grams. Since this is less than 5%, that will be an unusual event. If it is actually happened, then you may think there is something unusual about this sample. Maybe some of the 9 babies were born as multiples. What is it, multiples? Maybe twins or 3 babies in one birth. Okay, which brings the mean weight down. Or all of the babies are not European descent. In fact, the mean weight of South Asia baby is like this one. Or some were born before 40 weeks. All the babies were born at high altitudes. And some after this kind of calculation, we may find as long as the probability is less than 5%, we consider it's an unusual event. Then we can discuss something, or maybe the factor A, factor B, factor C change the mean of the body weight of those boys. Okay, let's move. Okay, example 6.5.3, finding probabilities for sample means. Okay, the age of American female first have intercourse is on average 17.4 years. Okay, with a standard deviation of approximately 2 years, like this one. This random variable is normally distributed, though it is somehow mount shape. Okay. I think we can take a look at this one and calculate the probability. Okay, like this one, like this one. Okay, and okay, let's move. Just a brief look of chapter number 7. Okay, and next week we will discuss something about the one sample inference. One sample inference. Then we will move to hypothesis testing. Okay, and if you think the normal distribution is difficult to understand, I promise you will feel more difficult about the hypothesis test. And we will run the t-test, pair t-test, independent t-test, something like this. Okay, and 7.2 one sample proportion test, 7.3 one sample test for the mean. Still, sure, we will not discuss the chapter number 7 here. Okay, any question? If no more question, how about you can study here, then we can have our course about 3 p.m. Sorry, our midterm 3 p.m. Is okay for everyone? Okay, so take a break, then we will come back to have our midterm at 3 p.m. Okay, see you later.